Okay, welcome to the review video on electronegativity for the common exam, which is happening in about 2 weeks. This is a super important video. You'll notice on the intro page here that I've actually provided you with a periodic table that has electronegativities in it. I would make sure to go through this video very, very carefully. You need to do it this week and not wait until the common exam. All right, now this is all stuff that we covered in class, but we're going to now go back through it. So by definition, electronegativity is actually one of your periodic trends, but in general, it is the least understood of the trends. So that's why we're going to go back through this in detail. So firstly, it's super important for you to understand the definition. Electronegativity only has any relevance at all when you're comparing the attraction two atoms have for the electrons that are in a bond that is bonding those two atoms together. That is the only relevance. This has nothing whatsoever to do with size of atoms. It has nothing whatsoever to do with ionization energy and so on. Electronegativity only has to do with the bonding electrons between two atoms. Period, period, period. The formal definition is the attraction an atom in a bond with another atom has for the bonding electrons that are between those two atoms. The trend: electronegativity increases left to right across the periodic table. So when you look at the table that is posted below, lithium has less electronegativity, for example, than fluorine. All right, electronegativity decreases down any group. So that means if we look at group 1A, that hydrogen has a higher electronegativity, say, than francium. Now, you're going to need to be able to apply these trends in a general way, utilizing the trends from the periodic table. Now, why do we care about this? You are going to use electronegativity differences in two ways to identify polar bonds in a molecule and to compare the relative polarity of individual bonds. We are going to do both of these in this video. Now I'm going to switch screens. In the first example, we're going to talk about how you identify polar bonds in a molecule. Firstly, you need to realize that there are molecules that do not have polar bonds. No polar bonds. These are the diatomics. All right, and over and over and over again this year, I have emphasized you must know the diatomics. So let's just take a quick example. I'm going to pull down the chlorine here, and I'm going to very quickly produce the Lewis formula, which should be absolutely no problem for you at this point. All right, so here is the structural diagram, or the Lewis formula. And why does this not have a polar bond in it? Because the two atoms that are involved in bonding to each other via these two electrons in this bond are identical atoms. So the CLs are identical. And the difference in En, electronegativity, is 0. So I'm to emphasize this: no polar bonds over here. None. 0. Kaput. Now, let's talk about the other molecules in the world, which is the vast majority of them. 99.999% of the rest of the molecules that exist on our planet or in our universe are going to have polar bonds. Why? Because those atoms that are bonded to make a molecule are different. They are different atoms. And if you're an atom on the periodic table, the likelihood that you're going to have a different electronegativity than another atom on the periodic table is highly probable, probably better than 99.9% of the atoms on the periodic table have most likely different electronegativities. So let's take the two examples below. First, and this is super important to you, I have no doubt you'll probably be asked about it. Here is an ionic compound. Ionic compound, and Lord knows you should know how to be able to identify those at this point. We have a metal that is bonded to a non-metal. These two atoms have extraordinarily different electronegativities. If you look back at the periodic table that I provided you on screen 1, the sodium has an electronegativity of around 0.8, what is it? It's 0.869 as an example, and the Cl has an electronegativity that is around 2.8, what is it? 2.869. This is an extraordinary difference between these two atoms, which is the whole reason why the bond that forms between the sodium and the chlorine is ionic in the first place. Why do these guys exchange electrons? Because the Cl in a bond with Na has an extraordinarily higher attraction for the bonding electron coming from the Na. All right. And any ionic compound is going to follow this rule. Let me go ahead and put that in words. It's going to follow this rule. Super important to know for the common. Super important. Now, so this was an ionic compound. Now let's turn the page and look at the covalent ones or the molecular ones. This is an example here. We have two non-metals in a bond. You should have no problem with this at this point. Be able to rapidly draw the Lewis formula, which is shown here on the right. The only thing I didn't do is put in the paired or the unshared pairs out here. So let me just do that really quick because that'll probably flip some of you out. Okay, now the structure in your world is correct. Okay, so this is a really excellent example of a typical molecular compound because the central atom is not the same as the external atoms. And you know well enough at this point, you can draw lots of different molecules, lots of different ones. And the one thing that they all have in common pretty much is that the central atom and even the external atoms can be different. And because of that, within these molecules, the actual individual covalent bonds are always going to be polar. And they're going to be polar because these bonds involve a covalent bond between two atoms that have a difference in electronegativity. They have a difference in electronegativity. So we essentially can say, in this case, the fluorine, if you look at the periodic table that was on screen 1, is to the right of carbon, and therefore it holds most of the electron density. So I'm going to use a little negative sign here in a parentheses to indicate a partial negative charge, and the carbon is going to be partially positively charged, partial charge, because the electron density of the bond is being pulled towards the fluorine, just like in example number 1 right here, except that for the ionic compound, the difference in electronegativity between the two atoms is so extreme that the Cl is basically got all the electron density. In the molecule down here, the fluorine has most of the electron density, but not all of it, because the difference in electronegativity between these two atoms is not as extreme as the NaCl example. All right, let's move to the next screen. Now, in this is the other scenario that you guys could run into, all right, where you have to rank and compare polar covalent bonds. So in example number 1, we've chosen, of all these bonds, we're keeping one of the atoms constant. So I'll go ahead and underline the atom all the way across this who is constant. And then what we're doing is we're making the partner to that atom in a covalent bond different. So in this case, we have, and what we're doing is we're walking across period 2 here. So in this case, the first bond that we're comparing is a C bonded to a boron. And then we have the C bond. And then we have a C nitrogen bond. And then we have a C oxygen bond. And then we have a C fluorine bond. Now, if you look closely, you can see what's happening here. The boron is far to the left of the fluorine, far to the left of the fluorine. And as we move to the right of boron, we come to carbon, then we come to nitrogen, then we come to oxygen, and then finally to the fluorine. So what are we doing? We're going left to right across the table, and the electronegativity is going up. So in terms of these relationships, all right, the CF bond is going to have the greatest polarity. Now, if you look at the table that I provided with you, and I know how you guys, a lot of you like numbers, you can see when you look at the boron that it has a electronegativity that is less than carbon. All right, so this is going to be the least polar bond. If you want to bust out a calculator and take the difference in electronegativities between these two bonds, you'll see that the delta En is not all that great. For the CC bond, of course, the delta En is going to be equal to 0 because the En for both carbons is identical. And then you can see what we have going on here. The nitrogen, the electronegativity is about 3, the oxygen is around 3.5, and the fluorine is approximately 4, a little bit over 4 actually. So this guy here is going to have the biggest delta En. So if we're going to rank these, we would say the CF is greater than the CO, which is greater than the CN, which is greater than the CC, which is greater than the CB. All right, moving down here to the bottom. All right, in this case, we're moving down a group. And we've fixed one of the atoms. So I'm using carbon as this example. And we're asking, okay, go ahead and rank these. So the carbon comes in, and granted, on the common exam, they're not going to give you a periodic table with electronegativities. But you have a table here on screen 1, and you can see that if you look at the electronegativity of carbon, it's about 2.5, and so the fluorine is approximately around 4, and the Cl is coming in somewhere around 2.8. And as we go down the group, as you know, the trend, let's see, what is this one? Is around 2.7 or so for this one, and then the iodine is around 2.4. So, but you know the trend already. You know that electronegativity decreases down the group. So if I was to rank these bonds, again, all of them are polar. If I was going to rank these bonds, then the CF is going to be greater than the CCl, which is greater than the CBr, which is greater than the CI. So it's very important. It's highly likely on the common exam you could be asked to rank bonds. And there's 2 ways that it's done. In example number 1, all right, what we're doing is we're going left to right across the table. In example number 2, we're moving down the table. In each case, some type of atom has been chosen uh, to remain constant for the comparisons. In this case, I used carbon in both number 1 and number 2 just because it was a convenient way to do the example. All right, with that, I'm going to go ahead and close the video.